We're going to be doing problem 13-16 from the fundamentals of chapter 13. Okay, so we have the problem gives us a 0.2 kilogram pin P, so mass is 0.2 kilograms, constrained to move in the smooth curved slot, which is defined by the lemniscate R equals 0.6 times cosine 2 theta. Its motion is controlled by the rotation of the slotted arm OA, which has a constant clockwise angular velocity. Theta equals minus 3 radians per second. That's theta dot. So constant angular velocity, thank goodness, because now we have theta double dot, which is 0 radians per second. And now it's determine the force arm OA exerts on the pin P when theta equals 0 degrees. So theta equals 0. Woohoo, nice. So what happens when theta equals 0? Well, if we look at this arm, right, this arm is going to be here, and the little ball is going to be right there. Okay, so let's just visualize it for now. So the r-axis is going towards the right, and then we know that theta has to be perpendicular, and we'll just do I guess we can pick this direction or whatever. So this is theta, okay, and it also coincides with the tangent as well, because at that point the tangent's going to be just straight down. Okay. So at that point we want to say, okay, what are the forces that are acting on that little ball? So if we look at this is pin P over here. Okay, well, we know there are a couple forces acting on it. We know the pin has a weight, right? And because it's sitting on this, the lemniscate, right? This it's sitting on the bar. It's going to be a force and theta on it. Okay, actually let me switch the direction of theta, just because they already established that clockwise is negative, so I'm just gonna keep it as a normal direction. So this is theta. Okay, so that's just to visualize what's happening to that pin. Okay. Now let's keep moving on with getting the equations of motion. So we know we're given r equals 0.6 cosine 2 theta. We know that r dot is going to be, let's see, if we take out the 0.6 and evaluate cos 2 theta, we're going to get a minus sine 2 theta. Okay. And then, what else? Times the derivative of what's inside, which is going to be 2 theta dot. Okay, so that's what we have ultimately. So we're going to have 1 minus 1.2, actually minus 1.2. I guess the cleaner way to do this, sine 2 theta dot. Okay, so that's our velocity here, our r dot. And then take another derivative. When we do a second derivative of this, we're going to have minus 1.2. Remember, kind of like I mentioned in the previous problem, we're going to evaluate this first times this plus all of this times the derivative of the second term. Okay, so it'll be cosine 2 theta times 2 theta dot, and now times theta dot plus, or I guess minus 1.2. Again, leave that first term alone and evaluate the second term, which is theta double dot, sorry. Okay, and that's it. We're done with the chain rule. We're done with that derivation. So now it's pretty simple whenever we have a theta double dot, because we know this term is 0. Okay, what else? We know that theta is 0, so when, you know, sine 0 is just 0, so then we know that this is going to be 0. Let me switch colors here so you guys can kind of see. So we know this is 0 because sine 0 is 0. Okay. So that pretty much leaves us with evaluating what r is, which is going to be, this looks like it's just going to be 0.6 meters, right? Because cosine 0 is 1 times 0.6. And the last term that we need to know is r double dot, which we end up getting as minus 21.6 meters per second squared. Okay, so we have our angular terms and our radial terms. Bada bing, bada boom. Okay, now let's move on to the equations of motion. So we have AR. Okay, so remember, write these down always. When you try to skip steps, that's kind of when you get into some trouble. So here we have minus 21.6, okay, minus r 0.6, and then theta squared, which is going to be times 9. Okay, and this gives us minus 27 meters per second squared. When we do a theta, okay, we have r theta double dot plus 2 r dot theta dot. Okay, and let's see, theta double dot is 0, okay, and r dot is 0, so there's no acceleration in the theta component. Okay, alright, we're almost there. So now let's do forces, forces in the, we're trying to get the force arm OA exerts on pin P when theta equals 0. So like I said, when theta equals 0, there's only 2 forces acting on it, and they're going to be in the theta direction. Okay, so we're going to have let's sum up those forces. It's going to be n theta, which is what we're looking for, minus mg equals mass times acceleration. But that term is 0, and then that leaves us with n theta times mg, which is going to be 0.2 times 9.81, 1.96 newtons. Okay, and that's it. You guys might be thinking, like, what? We had to do all that just to just narrow it down to just this last equation? It's like, yeah, but remember, think about it as practice, because your professor's probably not going to put something like this on the test. He's definitely going to put, you know, problems that you have to utilize all these elements, doing this first derivation, second derivation, and so on. But yeah, maybe not something like this. But yeah, that's pretty much it for this. You know, for the problems in this section. I'll try to do a few more from the actual problem set, just because a lot of people get lost here and they just pretend they okay, I think I understand it, I'll move on. They move on to the next section and they keep getting lost because they're just going to keep repeating. It's going to haunt you for the rest of the semester. Okay, so try to do these on your own. Follow along with the videos. I'll try to put out some videos from the problems from the text itself, you know, the numbered problems. And yeah, I'll see you guys in the next video. Don't forget to like and subscribe if you need to, and leave a comment down below if you have any questions. Thanks guys, appreciate it.